Luminescence is the emission of light from an excited state molecule. And as we see that this comes from the moving of the electrons from from an excited state into the ground state. And fluorescence and phosphorescence, the one that we have been talking about, are examples of luminescence. Um, in spectrophotometry, as we have seen before, we used to measure the absorbance of the light, and then we measured the absorbance of the molecule at certain wavelengths. In luminescence, in this case, we measure the intensity of the emitted light rather than the absorbed light. In this, luminescence is usually more sensitive than absorbance because it can detect even a single molecule. Because even a single molecule that will emit light, we can detect that. This is different from absorbance because absorbance only detect the amount that has been absorbed. So we detect a very small fraction that has been that is not that has been actually absorbed. We have two spectra here, excitation spectra and emission spectrum. Uh, as you can see from this graph, the one on the left, the black one, is the excitation spectrum, and it reflects the different wavelengths at which the electron will be excited from the ground state to the excited state. While the emission spectrum here is the one to the right, it's at higher wavelengths and it reflects the different wavelengths of the photons that have been emitted after the electrons have moved from the excited state to the ground state. The emission spectrum is actually a mirror image of the excitation spectrum, but at higher wavelengths. Let's try to understand why is it mirror image and why does this happen at longer wavelengths. So for absorption, the absorption spectrum or the excitation spectrum, you normally will have the electron at the lowest energy vibrational level of S node or of the ground state. And it will absorb energy or will absorb photons of certain energy, so of certain wavelengths. As it does so, it will be excited from the lowest excitation, from the lowest energy of S node to any of the vibrational levels of S1. So as it becomes excited, as you see here, it can go to any of these energy levels. The difference between the difference in energy between the lowest vibrational level of S node and these vibrational level of S1 are different. As it goes to a higher energy vibrational level of S1, that means this is a higher energy that will be absorbed. The photon will have higher energy, so it will have lower wavelengths because we know there is inversely proportion, the relation between the energy and the wavelengths. So we're going to have all of these energy difference, all of these photons will be absorbed and each will reflect the excitation from S node to S1. When emission takes place, first the electrons at any energy level of the S1 has to be to go back to the lowest energy level of S1. So excited electrons do not move from a higher vibrational level of S1 to S node. It has to go first to lose some of its energy first and go to the lowest energy level of S1. As it loses some of its energy, that means now as it jumps back to the S node, the difference in the energy will be less, and as you would expect, the wavelengths will be higher. So the electrons now is the excited electron is at the lowest energy level of S1. It can go back to the ground state, but when it goes back to the ground state, it can jump to any of the vibrational level of S naught. The difference in energy, as you see here, is varies depending on which vibrational level of S note it will go to, and that can be seen as excitation at as emission at different wavelengths. The smaller the difference in the energy, the higher the wavelengths. As you see, the lowest energy level at which the absorbance takes place is exactly the same as the highest wavelengths where the emission takes place, which is the difference between the lowest energy level of S1 and the lowest energy level of S naught. This is why the emission spectrum is the mirror image of the excitation spectrum, and it's at higher wavelengths because the difference in the energy here is less. In an emission experiment, we start off by having a light source, and then the light source will be polychromatic as well. So there are so many different wavelengths, and we need to get it through an excitation monochromator to choose only one wavelength for the excitation. And this goes through the sample cell, and as a sample, the molecules are excited, the electrons in the molecule are excited. Then when they lose their energy in the form of photons and they emit photons, this leads to luminescence, and we know that luminescence can have different wavelengths as well, so it emits photons of many wavelengths. So it also goes through an emission monochromator, so choose only one wavelength, and this wavelength will pass through a detector in order to measure the intensity of the emitted light. We have two types of spectrum, as we said. There is an emission spectrum and there is excitation spectrum. In emission spectrum, in emission spectrum, we have a graph of the emission intensity versus the emission wavelengths. So we measured the intensity versus the emission wavelengths. So we measured this one. For the excitation spectrum, is the graph of the emission intensity, but this time versus the excitation wavelengths, not versus the emission wavelengths. So an excitation spectrum is almost or nearly the same as the absorbance spectrum, because excitation means that it has absorbed the energy. So this excitation, the one at the left hand side, is excitation spectrum, and it's similar to the absorbance spectrum. In emission spectroscopy, we tend to measure the emitted radiation, not the absorbed radiation. So, as we said, for emission spectrum, it's more sensitive than the absorbance because it can detect even a single molecule. So an example of that is the fluorometric assay of selenium in Brazil nuts. So in order to measure the selenium in the Brazil nut, we take a certain amount of the nut and we digest it with conch sulfuric acid in order to get the selenium out of all of the other components. So digestion means that because the nuts itself, we cannot analyze it. We need to get a solution that has all the selenium, so we digest this with nitric acid. And then after digestion, we reduce the selenium product into selenite. So this is the one we are going to use. The selenite itself is not luminescent, is not fluorescent, so it doesn't actually give you any color or any emission. So we have to derivatize it, or we have to react it with with a fluorescent to give a fluorescent product. So we react it with a 2,3-diaminophthalein and at pH 2 at 50 degrees, that will give you a fluorescent product with the selenium. So this is the fluorescent product, and this is the one that we actually measure the emission of the emission of the luminescence of this product. It's not the selenium itself. Some analytes are fluorescent by nature, so they are naturally fluorescent, like the polycyclic aromatic compounds and riboflavin. So we don't need to devise it, or we don't need to react it with anything. We can measure it directly. Sometimes we need to make a compound with a fluorescent product or with a fluorescent moiety in order to get some product that is fluorescent. An example of that is fluorescein. So fluorescein itself is fluorescent, and we can use this to make complexes with other elements in order to measure their fluorescence. There is something called chemiluminescence, and chemiluminescence is the emission of light from a chemical reaction. So sometimes when you do a chemical reaction, you end up with a product that is luminescent, but the original compound itself is not luminescent. So an example of that is this dione, this compound, phthalazine dione, luminol. So luminol in itself is not luminescent, but when we do a reaction and we add an oxidant like hydrogen peroxide in under alkaline condition, and we with a metal catalyst, that will give us this product here, and this product is actually luminescent. That will lead to an emission of a blue light. So this is called chemiluminescent. So it's the emission of light from a certain chemical reaction, because the product of the reaction itself is fluorescent or luminescent, but the original compound is not.